right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about ESP32 PWM stuff. Oh, back up. No, hold on. There we go. Now it's better. What's up, guys? This is Dem Keys. I don't know how muted that uh beginning of the stream must have sounded. Let's try that again. What's up, guys? This is Dem Keys, and today we are going to continue learning about PWM stuff in the ESP32 using NoSTD Rust. Now, between yesterday and today, I have made a bunch of progress. Real quick, just so we have a tiny bit of movement going on, let me change this to 6 bits. Or should I? Yeah. No, yeah, wait, hold up. We're doing 20 bits, right? Let's take this down to 5 kilohertz. Or we could do 10 kilohertz, but then that becomes a very a very fast blinking kind of. You know what? Okay, let's do that. Let's try that and see how good or bad it looks. Okay, between yesterday and today, I've been doing a bunch of research. I've been trying to understand various things, including the little what was it? Fractional divider situation that we were having. It turns out that um, if the clock divider in the calculation, if yeah, so this is pulsating pretty fast, so I'm just going to slow it down a little bit and run it like that. Okay, so it turns out that if the clock divider value ends up being less than 1, so still a decimal number, but less than 1, then it just like defaults to um, or the PWM just defaults to a low signal the entire time. I should say, I guess the duty cycle, it just defaults to off the entire time. And this is according to Gemini. I'm yet to dive into the TRM. God, I keep accidentally hitting keys on my keyboard. I have like 3 or 4 keyboards beside me. I mean, one of them I guess I can't count it because it's far away and I rarely have to touch that. Um, but aside from that, I have 3 keyboards, and especially when I'm streaming, I have to like move keyboards around. And as I'm speaking, because I'm sitting on my bed right now, as I'm speaking, my hands move, and I sometimes poke my bed with my hands, or just making hand gestures. My hand is like tapping on the mattress and stuff like that. And because the keyboard is there, so I accidentally sometimes hit keys on it. Or if I go to grab the keyboard, like I tried to do just now, I accidentally hit some of the top keys of the keyboard, like the F keys, F1, F2, and so on. It's it's weird. Okay. Anyways, so just did it again. I'm just hoping that I don't accidentally, at some point hit just the right key combo to stop the stream. I hope that doesn't happen. But anyways, what was I saying? Yeah, so according to Gemini, if the clock divider ends up being less than 0, and you know what? Hold on. No, wait a minute. I'm remembering something right now. Actually, this is mentioned in 2 places. One place is here in this tutorials thing. This tutorials thing, quote unquote, is the Impel Rust for ESP32 book. This book has been a gold mine for me. I discovered this book towards the end of last month, towards the end of, what was it, March? Yeah. I discovered this book towards the end of March. Prior to this, I was heading into this very much blind, and I was gonna have to like explore this on my own, and holy shit, things would have been significantly harder if I didn't have this kind of a resource to explain these things. Because the things that were explained in this resource, these things gave me some knowledge, and well, actually, no, all in all fairness, this resource gave me a lot of knowledge, and then I built up on that knowledge a lot more by reading the TRM. So there were certain things that I got curious about after reading, this resource, and then I decided to uh, look at the TRM to learn a bunch of to learn more in detail about what is being taught here. So yeah, this has been a gold mine for me. Why was I talking about how much of a gold mine this is? I think I was talking about like this book. The name is Impel Rust for ESP32. By the way, anyone who's looking to get into ESP32 development specifically through Rust, absolutely look up this book. It's a free book. It's a free resource developed by a community online. It's not just for the ESP32. They've made one for this. Okay, so this focuses mainly on no STD Rust. That's the special thing about this. It doesn't rely on like some sort of heavy framework sitting on top of the bare metal. You are basically running all of your stuff on bare metal. um what was I saying? Yeah, so just like we have Impel Rust for ESP32, there's Impel Rust for STM32, for I think for Pico. I believe that's for the Raspberry Pi Pico. And there was one more mentioned. I can't remember what. Oh, you know what? There's uh the GitHub repo is there here. I'll just open that up. Impel Ferris. This is the um why does that say that? Give me a second. Oh, okay, never mind. Yeah, Impel Ferris. This is the community um that is, or well, this is, I don't know what to call this, an entity, but this is being it's being contributed to by volunteers. This is where you can, as it mentions here, a collection of Rust projects, learnings, and experiments. In our case, we are specifically focusing on um, embedded programming. So there's Pico, there's RP 2040. Okay, they've mentioned Pico and RP 2040 separately, but RP 2040 is the chip that goes on the Pico. So like, what's the difference here? Hold on, I'm curious about this. Um, you know what? Instead of Googling it, I think I'll just ask Gemini. Pico versus RPi, no, Pico versus Pico 2 versus RP 2040. Because my understanding, not 2024, hold on, 2040. Yeah, my understanding is that RP 2040 is the chip, just like how ESP32 is a chip, and then we have, a module that the chip is on, and then the module is on a dev board. I was assuming that that's the case. Okay, so let's see what Gemini said. The Raspberry Pi Pico 2 is a significant performance and security upgrade over the original Pico. While the original Pico is powered by the RP 2040 chip, the Pico 2 introduces the new RP 2350 chip, which nearly doubles the memory and adds a unique dual architecture option. That's interesting. Okay, I had no idea. I had no idea about this. I only knew about the RP 2040. I should look into this. Let me hold on. Now I'm curious about how cheap or expensive this might be. Um, RPi Pico 2. Give me a second here. I want to see at what price I can get this. I mean, I'm still going to stick with the ESP32 because there's so much for me to explore here that I have very little reason to, you know, go into the other stuff. But then I don't mind exploring the other stuff. It's not expensive. I wouldn't say it's expensive, but it's not as cheap as the. Hey, no, you know what? Hold on. No, I take that. Well, yeah, no. It's not that it's expensive. It's just not as cheap as, you know, let's say an ESP32C3 Super Mini, and I'm guessing it also has more in terms of more to offer in terms of hardware resources. Let me see what. Wait, where's the conversation that I was having? Oh, here it is. The RP2350 chip in the Pico 2 provides 512 KB of SRAM and 4 MB of onboard flash, doubling the capacity from the original RP2040. This is ideal for more complex code and larger data buffers. Then there's something security related as well. Then interfacing. The Pico 2 adds 4 more programmable I/O state machines. Okay, you know what? Okay, this has been mentioned previously when I was trying to compare stuff like CH32 and STM32 and ESP32 and also RP2040. This was being mentioned that apparently this is something special in the RP chips specifically. Um, I was just assuming programmable I/O means like, being able to program the GPIO pins, which you can clearly do in a bunch of microcontrollers. Um, let me try asking that question as well. Give me a second. I just realized that I forgot to open up my chat on my phone. So I'm gonna do that real quick, and then we can continue. Right. Okay. So, um, where was I? Oh, yeah. Hey, so I'm looking into RPi Pico. I'm coming from an ESP32 background. I've seen programmable I/O be mentioned as something special in um, RPi RPi Pico. I'm confused because how is this different from being able to program the GPIO pins on the ESP32? Coming from the ESP32 world, the confusion is totally fair. On most microcontrollers, including the ESP32, when you want to quote unquote wiggle a pin to talk to a sensor, you either use a dedicated hardware peripheral or you resort to bit banging. Okay, all right, that's fair. So if we want to use PWM, we use dedicated PWM hardware, and that dedicated PWM hardware has, the it has the in our case specifically LEDC. The dedicated PWM hardware is our LEDC, and then that has the high speed group and the low speed group, and in each of those groups you have a set of timers and a set of channels, and the channels are what send stuff out to the pins, right? So the work is not being done like at the pin itself, it's being done by the hardware and then being routed to the pin. So then how is this different? Okay, programmable I/O is a third way. It essentially it's essentially a set of tiny stripped down processors dedicated. Oh, wow. It's essentially a set of tiny stripped down processors dedicated solely to handling data coming in and out of the pins. The core difference, CPU versus PIO. On the ESP32, if you need to support, oh, wait, give me a second. Okay, all right. What was I saying? Wait, give me a second. Let me make sure we are not dropping any frames. Yeah. So, uh, what was I saying? Yeah. Okay. This seems like a newer way of doing things, and I'm glad that I looked into this whole dedicated PWM hardware stuff because I wouldn't have understood this otherwise. Okay, on an ESP32, if you need to support a weird non-standard protocol like a specific LED strip or an give me a second. Okay. Yeah, what was I was reading this. Okay, like a specific LED strip or an old camera interface, your main CPU has to do the heavy lifting. The bit banging problem in the ESP32, when you bit bang, the CPU is manually setting pins high and low. If an interrupt happens, like a Wi Fi packet coming in, the CPU pauses your wiggle, the timing breaks, and your data gets corrupted. The PIO solution with Raspberry Pi Pico, the Pico has two PIO blocks, each with four state machines. You write a tiny piece of code using just nine basic instructions and push it to the PIO. Once it's running, it handles the timing with cycle perfect precision without even bothering the main dual core CPU. That is crazy. Holy shit. Okay. Why Why is PIO special? Think of PIO as a way to build your own hardware peripherals using software. Deterministic timing, PIO instructions always take exactly one clock, one clock cycle, or a fixed amount you specify. There's no jitter. Offloading. While the PIO is busy pulsing an electronic sensor, and sorry, an ultrasonic sensor, or driving a VGA display, your main CPU cores are 100% free to do math or handle logic. Then FIFO buffers. The CPU just throws data into a mailbox or FIFO, and the PIO picks it up and sends it out when the timing is right. Okay, real world examples. WS2812B NeoPixels. On the ESP32, you typically use RMT, you typically use the RMT peripheral or a library that uses a lot of CPU cycles to get the timing right. On the Pico, you can write a 5-line PIO program that handles tight timing that handles the tight timing of the NeoPixel protocol. You can then drive thousands of LEDs without the main CPU even breaking a sweat. How it works in practice. You write PIO code in special assembly-like language, example set so-and-so pins to so-and-so, which says set the pin high and wait for 5 cycles. This gets compiled. I'm assuming they've made like a Rust equivalent of that. See, now I'm curious. Now I'm curious about this because, like, okay, we have two things here. We have the RPi Pico 2 and we have the RPi 2040. The 2040 is much cheaper. I remember seeing that. So RPi uh, Pico. And there was also a Pico W. I don't know what the difference is there. I'll have to look into that. But yeah, these are significantly cheaper. These are actually cheaper. Much cheaper. So if these happen to have the PIO pins, I would be interested in this because this is crazy. Holy shit. Though that being said, this is a different working mechanism. This is a different architecture overall. So I don't know. Let's take a look. Let's take a look at the repo and go to the Impel Rust thing. this is actively being maintained, which is amazing. All right. So, give me a second. Let me get the zoom right. Okay, meet the hardware. Wait, in the dev environment, what all do we have to install? Because there's going to be a new tool chain to install, right? Sudo apt install so and so, so and so. Okay. Embedded. Okay, RPi Pico SDK. Submodule update so and so. Build and install Pico tool. Okay. Then Rust targets. We need to install the targets. We need probe RS. We need probe RS. However, so we can get probe RS, but like, okay, it says it supports ARM and RISC-V targets and works directly with our, it works directly with hardware debug. When you use a debug probe with Pico, probe RS is the tool you rely on for both flashing firmware and debugging. Okay, all right. Nix OS. All these same steps can be achieved on Nix OS with so and so. I'm not using Nix OS, so I think I'm good. Quick start. Okay, I'm wait, for the time being, I am curious about the PIO. So, and here also, I'm glad that they have this. So, from STD to no STD. We have successfully flashed and run our first program, which creates a blinking LED effect. However, we have not yet explored the code or project structure in detail. In this section, we will recreate the same project from scratch. I will explain the part so and so, so and so. Okay, all right, great. Wait, do they also have like a TUI that you do they also have a TUI that you use for what's under abstraction layers? Okay, cool, cool. So we have our HAL, then we have peripheral access crate. This I don't need to touch. The microarchitecture crate. I think I just opened something. Let's close this. Okay. Then we have, okay, that's our microcontroller with the processor, peripherals, and so on. Board support package. That's what I wasn't able to remember. Um, okay, all right. So far we are good. No main, flashing, blinking LED. Let's take a look at what, you know what? Not all that different, to be honest. Actually, if the HAL being used implements embedded HAL, then I think the API would be much more similar. Okay, okay, button, PWM top. Okay, okay. Servo motor, Bazinga. I like that. Voltage divider, ultrasonic, interrupts, I2C, OLED. Okay, yeah, this is our typical, what we do in the other one as well, in on the ESP32 side as well. As in the tutorial on that side as well is, oh, there you go, PIO. This is one of the features I avoided for a long time on the Raspberry Pi Pico, yet it is one of the most powerful and unique features of the chip. Not because it was difficult to understand, but because it was not clear where it actually fit. The Pico already has SPI, I2C, and UART. So the first question that comes up is, why would you need something else? The answer is not about replacing those things. It's about what happens when they are not enough. So essentially, when you need like a custom solution. Um, okay. I'm gonna try and understand this because I have like limited knowledge now. I understand the crystal part. We also have an internal oscillator, so there can be clock signals being generated in two ways. That goes into the PLL. I'm assuming that then gets hold on. It's not going to anywhere from here. Okay, I'll have to read this to understand like what's going on. Let's continue. Well, I'll have to read up more on the architecture of this RP 2040 hardware in order to understand what's going on here. Um, but I'm going to continue reading this. I actually mainly just want to know what the code looks like. Okay, let's see what this person is saying. What is PIO? PIO stands for Programmable Input Slash Output. It's a set of small processors built into the RP 2040 chip itself. They are not the main CPU. They run on their own at the same time as the CPU, and they do one thing: move data in and out of GPIO pins with exact timing. On most microcontrollers, if you need to talk to a device that does not use a standard protocol, you have to do it on the main CPU. You write code that turns pins on and off at the right times. This is called bit banging. It works, but if something interrupts the CPU, even for a short time, the timing can break. The device on the other side does not care why, it just stops working. PIO fixes this. The state machines inside PIO run their own small programs, completely separate from the main CPU. The timing stays the same no matter how busy the rest of the system is. The RP2040 has two PIO blocks. Each block has four state machines. That gives you eight in total. Each one runs its own program. Each one can control pins on its own. All right, okay. Use cases. PIO is not something you need for every project. If your parts use I2C, SPI, or UART, and you have enough ports, just use those. PIO is for when that is not enough. All right, okay, okay. Let me see what the example code looks like, how it works. Okay, okay. Let's get into some of the code. I need to see. Using PIO for blinking, so and so. Okay, we start with a minimal PIO program that runs and wait, we are legit writing like the assembly that it requires. So how does this fit in with our main Rust program? Also, I like that there's a simulator for this. Yeah, there's a simulator for this. That's dude, that's cool. Um, okay, instruction delay. Okay, okay, okay. No op. All right. Yeah, we are legit writing assembly for this. That's crazy. Using PIO for blinking so and so and embedded Rust. Okay. Is this going to be like an assembly block sort of thing? Like you can write raw assembly in Rust. I wonder if they've set up something similar. Um, this is an interesting way of I don't think I've ever done this in Rust. Like let this and then curly brackets here and then equals this. Um, yeah, no, I'm a bit confused about how this syntax is working. Anyways, moving on, defining, yep, there you go. So we define the assembly program in this way. All right, all right. You know what? This is great. This is great. It's not what I need to be getting into right now. So Give me a second. I'm just gonna go back. We are here, and we do this and this, and sorry, zoned out. Um, okay, Pico. Okay, okay. Yeah, I think we are good. I do need to open up these the well, this PDF in different sections though. What was this? Oh, okay. All right. So let that load up. Um, give me a second here. Right. So, yesterday I was doing research on a bunch of things, including the clock divider, why in our case this thing wasn't working. And I just remembered what I remembered earlier in the stream, which I was about to say, but then I kind of got distracted. Give me a second. There was clock divider was mentioned somewhere here. Yeah, the division factor ranges from 1 to 1023. It doesn't mention anything below 1. So I'm assuming that if it's below 1, it just defaults to 0. Or the duty cycle, it gets set to 0. The duty percentage gets set to 0%. So the entire time your signal is just it's off. Or I don't know if yeah, like what would the because like with a division factor of 1, it goes full speed, right? Isn't that what they mentioned here? Yeah, so here we have a division factor of 1. So here we are calculating what the highest resolution, and we are saying it's the clock source divided by um, our PWM frequency multiplied by the clock divider. And the clock divider, it says, it mentions somewhere here. The highest resolution is achieved when the clock divider is set to 1, meaning no division is applied to the clock. It is calculated as so and so. So if no division is being applied to the clock, that means we are running it at 80 megahertz. Though, though, there is no, there's something. There's a. Would it be running at 80 megahertz? I don't. I don't think so. Wait. Let me try asking. Give me a second. Okay, in the ESP32. No, I'm doing ESP32 development with no STD Rust using ESP HAL. Um, in LEDC, if I set my duty resolution and PWM frequency such that the clock divider ends up being less than 1, um, I've read that the PWM duty percentage just gets set, or okay, I shouldn't say that it's because of the duty percentage. I've read that the PWM signal just stays low. Wait, what was my question there? Oh, So does this mean that we've got an 80 megahertz um, low PWM signal being shot out? That's a sharp observation. When you're diving into the weeds of no STD. Wait, no, hold on. I'm still setting a PWM frequency. I just words. Holy shit! I just realized that we are still setting a PWM frequency, but then our clock divider is set to one. If our clock divider is set to one, and let's say we do, yeah, okay, it's mentioned here, right? 80,000. 80,000. That's going to be our highest. That's going to be our number of ticks for each cycle, I'm assuming. Because what are we doing here? We are dividing 80 million into chunks of 1,000. We are dividing 80 million into 1,000 chunks, 1,000 pieces, 1,000 groups. So how many items are we going to have in each of those groups? That is 80,000, and that is the number of um, ticks that our counter has to reach in order for it to count as one cycle, one period. But that does mean that we are running at yeah, yeah, dude, no, that does mean that we are running at 80 megahertz because we are dividing 80 million our by our frequency. Yeah, that's right, isn't it? Okay, let's see what Gemini is saying. When you're diving into the weeds of no STD rust on an ESP32, you're essentially dancing on the edge of the silicone's limits. To answer your question directly, no, you aren't shooting out an 80 megahertz signal. If the clock divider calculated for your LEDC configuration is less than 1, the hardware essentially breaks its internal timing logic. Here is what is happening under the hood. The math of the LEDC divider. Okay. Sorry, zoned out. All right. The LEDC peripheral calculates the output frequency based on the source clock, the clock divider, and the duty resolution. Based on the source clock, the clock divider, and the duty resolution. When you request a frequency and resolution that forces the div less than 1, the hardware cannot fulfill the request because the divider is a fractional counter that must be at least 1. What actually happens to the signal? When the configuration is invalid, the PWM generator typically fails to toggle the output flip-flop. Logic state, the output isn't oscillating at 80 megahertz. Instead, the internal counter never reaches Instead, the internal counter never reaches the threshold required to flip the pin state. The result, the pin stays, the pin remains at a static logical low. It is effectively a dead line. It isn't a high frequency signal. It's the absence of one. Okay, that's good enough for me. I'm still curious to see if I can find this in here because we need what's the register? LEDC clock div num HS timer. Okay, let's read this. Let's see if anywhere in here we get the answer. Also, this was where I had seen this thing like you divide the value by 256 to set a certain. Actually, I'm curious about that. I did open up this conversation with Gemini before, so I guess I can go back and look at that conversation. Let me just. Okay, this is clock divider. Um, there, math for bit manipulation. Okay, the logic boils down to the fact that every bit in a binary register represents a power of 2. Because of this, multiplying or dude, I should do this off stream. This specific thing I should do off stream. I just remembered that. I'm gonna keep this in mind and look at it off stream. Let's continue with this. So the clock for each high-speed timer LEDC clock has two clock sources, a RefTick or APB clock. Okay, for more information on so and so, that's fine. The input clock is divided down by a divider first. The division factor is specified by LEDC clock div num. That's the one that we had seen, which contains a fixed point number. The highest 10 bits represent the integer portion A, while the lowest 8 bits contain the fractional portion B. The effective div the effective division factor LEDC so and so is as follows. So we get an integer number for this. So if our division factor is, wait, no, how are we representing the fractional portion of a number? Like how are we doing that? Because the fractional portion would then be represented as 0 point so and so, right? And then the integer portion would just be represented as, so if it's I don't know, 512 by 512 point 232, right? 512 would be the integer portion, and then 232 would be the fractional portion, wouldn't it? Though I guess I need to look into how fixed point numbers work, because there might be some information I'm missing about how these numbers are represented internally, and that's probably why I don't fully understand it. Okay, that being said, um, the division factor ranges from 1 to 1023. When the fractional part is not 0, the input and output clock of the divider is shown is shown as in figure 28 2.3. Okay. Among the 256 output clocks, B of them are divided by A plus 1, whereas the remaining 256 minus B are divided by A. Output clocks divided by A plus 1 are evenly distributed in the total 256 output clocks. I have not understood this math at all. I do want to learn about fixed point numbers and how they are represented, because even with the floating point numbers, the binary representation is interesting, because there's like um you have a different way of you have a different way of representing the decimal point. You don't exactly write it as, so and so point so and so. You represent it in a very different way. Okay, the output clock of the divider is the base clock. I don't think it's mentioning here what happens if the thing is 0. The lowest resolution. The lowest resolution is calculated when the clock divisor is so and so and rounded up. If the lowest resolution calculated by the formula is lower than 0, then the lowest resolution should be 1. See, I haven't fully understood this. However, I don't want to keep digging for information here because I feel like that's going to waste a lot of time. What was it called? LED I think it's this. No, it's not this. It's LED clock div. No. Yeah, clock div num HS timer. Let's see if we find it here. LED clock div. Hold on. I'm just scrolling through this entire thing to see if I see that. There. The register used to be used to configure the division factor of the divider and so and so. Yeah, even this doesn't mention. I just need like a proper confirmation from even elsewhere. Okay, let's try this. ESP32 um, PWM clock divider less than 1. Okay, one way to test this out is since we know the math right now, we can how do we do this? So we have our what was it? APB clock divided by the frequency multiplied by what? What was our formula? I forgot. Our frequency multiplied by the duty resolution. Okay. All right. So we know our APB clock. That's fine. Okay. We now that we are getting this tiny clock division factor, we can try either increasing the resolution. Let's try increasing it to 25,000. That made it smaller. Holy shit. Okay. Let's make it 500. So now our thing is increasing. 50, now we have 1.5. Let's do 250, 0.3. Let's do 200. Now it's, 200, that's 0.38. Let's do 100, 0.7. 75 is that. So with a duty resolution of 20 bits, we are going to try, what was it? 25, right? 75. Um, we're going to try 75 hertz. Okay, and let's see if this works. We've set a duty resolution of 10, sorry, a duty percentage of 10. So it should be a pretty dim light. Though, I mean, 75. I feel like, because I've noticed that I think anything past 50, you start to, your eyes start to average the thing out. I'm not sure. Okay, while this is happening, let me hydrate and then I'll continue. Okay. Right. So, um, let's try. Wait, first of all, just to confirm that this is, you know, working how I am assuming it's supposed to work. Let's see if the LED becomes dim now, or well, lights up dim. Yeah, it does. Okay, awesome. Okay, cool. So now between 75 and 100 is actually 100 is also too much. So let's take it to 76. 76 would still work. Let's do 77. That's where it should break. Okay. Let's hold on there. Let's change this to 77. And if it doesn't work, then we know that it's because of the clock divider. Dude, I don't even remember how I got this the formula for calculating the clock divider. I think it was Gemini that gave me the formula for it. I mean, it's also I'm pretty sure it's also mentioned here. But like I didn't understand. Yeah, there you go. Okay. It's not working. Let's change this to 76 and see if it lights up. Okay, now while this is doing its thing, I'm going to scroll back up and we're going to look at, okay, that's our duty resolution. This is our clock divider. This I didn't understand. So this didn't really help me. Okay, it works. So that kind of that kind of solidifies it. That kind of proves that it is indeed the clock divider. I'm actually I'm part of the Rust Discord, and they have an embedded programming section. I could try asking there. Yeah, I could try asking there. Um, but okay, we can run a couple more tests. Give me a second. Sorry, zoned out. Okay, we can try increasing the resolution, sorry, increasing the PWM to, let's say, 25,000. Okay, that makes our division factor tiny, but then we can try reducing the duty resolution. So let's make it maybe 10. Okay, that's already good enough. Is that good though? Like, will that work? That works, right? That works because it fits within that category. It fits within that range that we are supposed to be within, which is 1 and 1023. So this should work. We can plug in those numbers and what did I set that to? 10 bits and 25K. Oh God, what did I just do? Okay, 25 kilohertz. Okay. And we can set the duty percentage to 25. It doesn't have to be so dim. This is great. This is great. We're making progress here in terms of understanding how these things are working. Okay, so that's going to be our PWM. That's going to be our clock divider. Hold on. Once this uploads, let's see if it turns on. It doesn't turn on. No, we have a problem. We have a problem here. It does not turn on. What happened? Did I miss? Oh, yeah, that's my fault. I didn't set that to 10 bits. Now hopefully it'll work. Okay, while we are doing this, we can increase this to, let's say, 50. Okay, that works. Let's say 150. That doesn't work. Can we actually? Well, okay, it's 150 kilohertz. So yeah, we should still be able to do that. We should be able to do that. What is like the max speed of the PWM? And yeah, okay, this works. Great. So that answers that question. So we have 150 kilohertz. In order to make 150 kilohertz work, we would need to reduce the duty resolution. So we can say 9 bits. So let's try that. So this is 10. Uh, Now we make it 9, and this becomes 150 kilohertz. Oh, dude, I need this upload process to be faster. The thing is, I have no idea how I can make this any faster. Okay, that works. Great. Awesome. Uh, Here, here. Okay, all right. Um, let's try going higher. Okay, can we, okay, what if we do 550? We definitely need to turn down the resolution. By not that much, actually. Hold on. Yeah, we didn't need to turn it down by all that much. Okay. So we can do 7 bits. 7 bits is still pretty decent, isn't it? Well, okay. I mean, whether it's decent or not depends on the resolution, depends on the application, depends on what we are trying to do. Let's do 750. Okay. Give it a little breathing room, 950, and we can do 1 megahertz. One, yeah, one megahertz. Is this 1 million? Okay, now I need this. Okay, that works. And then we get only 32. So do we have a function for that? We do. So that's 1 megahertz. And we change this to 5. Okay, it works. Great. Okay, you know what? I'm curious about this. Let's try fading this. Let's try fading this with this code. and look at what that fade looks like, because our steps are in what are so the steps are like, okay, so we have let's say 32 steps, right? um if we set a duty percentage of if we set a duty percentage of 25, that's going to go up to, so if it's 32, 16, 8, that's going to go up to 8, and then, or it's going to remain up for, 8 number of ticks, and then it's going to go down. Actually, wait, it's going to go up and then it's going to go down, but then it's going to repeat, it's going to keep on doing that a million times a second. So how's that changing anything in this case? Because in this case, it's actually changing the duty fade. Like this function is changing the duty fade. Wait, um, hold on. Okay, okay, yeah. Let me just start uploading this, and then I can continue thinking about this. So let's see what the quality of this looks like, because I'm trying to think of like what that would look like. It counts to 8. It counts to 8 and then goes low. So it remains high for 8 ticks. It's not doing anything. It is not doing anything. Okay, let's try taking this down. Let's go to 9 bits and take this down to, I don't know, 500 kilohertz. Actually, does that work? Let me plug the numbers in. We do 9 bits and 5,000. No, 500,000. No, that's not going to work. I need to take it down to 50,000. Okay, let's do that. 50,000. Okay. We can see the fade happening. We can see it at 50 kilohertz, but at 1 million, uh, at 1 million hertz, at 1 megahertz, I don't see it. Oh, sorry, zoned out. Okay, okay, I'm doing ESP32 projects. If I set the LEDC, what is it? Duty. No, what am I trying? Oh, LEDC PWM frequency to 1 megahertz, and try to do a fade effect. I should say when I set so and so and try to do a fade effect. Why am I not seeing a fade? Okay, setting a PWM frequency to 1 megahertz on an ESP32 is a bold move. While the hardware can technically handle it, You've likely hit a fundamental wall involving duty resolution. In short, a 1 megahertz at 1 megahertz, your ESP32 has almost zero room to create the subtle steps needed for a fade. The resolution versus frequency trade-off. The ESP32's LEDC peripheral operates on a fixed clock. Okay, this is gonna explain the entire thing to me. Wait, um, I've set duty resolution to uh, five five bits. It was 5 bits, wasn't it? Let me confirm. Yes, it was 5 bits. Here I've set duty resolution to 5 bits. So I know the clock div is greater than 1. The thing is, with 5 bits, you only get 32 steps per period. I'm not sure how this impacts the quote unquote illusion in any way. You've hit a classic wall with PWM on the ESP32. While 2 to the power 5 equals 32 steps sounds like it should be enough to see some change, the issue isn't just the math. It's how the human eye perceives light versus how the hardware handles high frequencies. Here's why your so and so thing is fading. The logarithmic perception gap. The biggest culprit in the human vision is logarithmic. What? The biggest culprit, the biggest cult words, holy shit. The biggest culprit in is that, okay, the biggest culprit is that human vision is logarithmic, but PWM duty cycle is linear. When you only have 32 steps, that is 0 to 30, 31, the jump, quote unquote, in perceived brightness between duty cycle 1 and duty cycle 2 is oh, the uh the blink is happening way too often. Is that it? The blink is happening just way too often. So like, is it that it's happening so often that it all just blends together? Though, how is it blending together when the duty cycle is set to 1 or 0 or 0%, 1%, whatever, low percentage? How is it still appearing the same when the duty cycle is low? Yeah, yeah, that would be interesting to explore. Like, what exactly is happening there? Okay, okay, let's continue reading here. In perceived brightness between duty cycle 1 and 2 is massive. Wait, when you set only 32 steps, the quote unquote jump in perceived brightness between duty cycle 1 and 2 is massive, 100% increase in power. However, the jump between 30 and 31 is barely noticeable, about a 3% increase. I didn't get that. Between cycle 1 and cycle 2. So, okay, hold up. When you only have 32 steps, the quote unquote jump in perceived brightness between duty cycle 1 and 2 is massive. Between duty cycle 1 and 2. Okay, so I'm assuming they're talking about periods. So period 1, period 2. Um, or well, they could be talking about the in each cycle, the amount of like on time, the specific on time portion. They could be talking about that, maybe not the entire period. That could be it as well. Oh, give me a second. We are dropping frames. Let me do something to fix this. Okay. I think we are good now. Yeah, I think we're doing better. I also just realized this. I throughout this stream have not once um oh my God, oh shit. I've gone through hold on. That's crazy. I've gone through an hour and 10 minutes of stream with like um I don't know, a 10-second delay on this RTMP feed, and now we have a 1 or 2 second delay. That's crazy. That is crazy. Well, anyways, um, okay. So what Gemini is saying here is that um, the jump between duty cycle 1 and 2, so the portion of period 1 that is high and the portion of period 2 that is high, the jump between these two is or the perceived the jump in perceived brightness, I should say, the jump in perceived brightness between these two is massive. So you see a massive increase. However, between 3 and between 30 and 31, it's barely noticeable. With only 32 levels, you lose all your granularity in the dim range where the eye is most sensitive to change. To the eye, the LED will seem to snap to mostly on very quickly and then stay there. Okay. All right. So it's doing what it's supposed to do, but once we go to a high enough speed and more importantly a low enough resolution, the illusion kind of starts to fall apart, and it all just like blends together. Okay. The resolution versus frequency trade-off. The ESP32's LEDC peripheral relies on a high speed source clock, usually so and so. The hardware formula is so and so. At 1 megahertz with 5-bit resolution, you are pushing the limits of the hardware's ability to divide the clock while maintaining a clean signal. While a 1 megahertz toggle is easy for the ESP32, the sampling rate of your fade, uh, how fast the how fast you update your 32 steps might be interfering with the carrier frequency. This is interesting. Okay, why 1 megahertz is overkill? Sorry, I was just reading the thing and all of a sudden I just got like quiet because of that. Why 1 megahertz is overkill for fading? Unless you are building a high-speed switching power supply or an induction heater, that's holy shit. Okay, 1 megahertz is far too high for an LED. Okay, two reasons. Parasitic capacitance. At 1 megahertz, the rise and fall time of the ESP32 pins and the internal capacitance of the LED slash wires starts to matter. The square wave starts looking like a series of rounded humps. Okay, all right. Effective range. Because the pulses are so short, 1 microsecond total period, the LED may not even have time to fully saturate or turn off before the next pulse hits, effectively blurring your duty cycle into a flat DC voltage. Okay, this is a combination of things. Okay, all right. How to fix it? To get a smooth, professional looking, quote unquote, breathing or fade effect, you need to shift your parameters, increase the duty resolution, or and lower the frequency. And use a gamma correction table. Instead of incrementing your duty cycle by 1 each time, use a lookup table or a mathematical function to apply gamma correction. This makes the fade appear linear to the human eye by spending more time/steps in the lower brightness values. That is something I should look into at some point later. I didn't think about this. But okay, so am I wait. So am I understanding this correctly? Um, the reason it's not working is a combination of factors, including the illusion falling apart, um, the signal, the signal getting distorted and more. Exactly, you've hit the nail on the head. It's not just one thing failing, it's a perfect storm of hardware, physics, and human biology working against you. To visualize why the 5-bit resolution is killing the illusion, look at the difference between a linear ramp and how our eyes actually perceive light. You know what? I'm going to stop here. Wait. Before I get sucked too deep into this, um, I'm going to stop. We know now that 1 megahertz is way too high. We're gonna stay within the lower range. Um, the next thing that we were supposed to do, because now that we understand the clock div thing, I mean, I still have my doubts about it, but like we've tested out the clock div thing, right? Um, now that we know this, now we can get the right values. Now we can calculate the right values, and dude, I still can't remember where I got the clock div formula from. Hey, can you tell me where in the ESP32 TRM is the clock, is the LEDC PWM clock div calculation formula? Because I remember getting it from you, and the formula is APB underscore clock divided by F underscore PWM. So let's say PWM underscore frequency multiplied by duty underscore res. And this works great for me. However, I can't seem to find it in the TRM, so I'm not sure if I would have even known about this unless you had told me. The the TRM does mention another formula, which is A plus B, or, well, yeah, A plus B divided by 256, where A is the integer part of the 18-bit register and B is the fractional part. Okay, let's see what Gemini says. Okay, finding that specific formula in the ESP32 TRM can feel like a scavenger hunt, because the TRM describes the hardware from the perspective of register values, whereas my formula describes it from the perspective of application goals. The TRM won't explicitly show you PWM equals, oh God, I just hit my keyboard. It won't show you that exact formula in a single box, because that formula is the result of how the hardware counters behave, where it lives in the TRM. You're looking in the LEDC PWM controller chapter, usually chapter 13 or 14. The formula you found, A plus B divided by 256, is the clock divider. This is how the hardware takes the 80 megahertz clock and slows it down before. Oh, wait, this is, yeah, that's the clock divider, isn't it? That's the clock divider. Or that's also what we are calculating here, right? Yeah, yeah. Um, it slows down before, wait, what? This is how the hardware takes the 80 megahertz source clock and slows it down before it hits the PWM counter. The TRM defines the output frequency using this logic. The source clock is divided by the clock divider. The result is so and so. Connecting. The result is then divided by the total number of steps in your PWM cycle, which is your 2 to the power bit res. Okay. Um, Connecting the dots. If you combine the TRM's logic into one algebraic equation, it looks like this. Why my formula looks different? The formula I gave you is just the algebraic inverse. TRM perspective, if I set these register bits, what frequency do I get? User perspective, I want this frequency, what do I set the registers to? If you set the fractional part B to 0, the TRM formula simplifies perfectly to the one we've been using. Oh, okay, okay. All right, how you would have known. Honestly, most developers don't find it in the TRM at first. They find it in the ESP IDF header files or the API reference. If you look at the source code for LED set frequency and so, you will see the engineers doing exactly that math, taking your desired frequency, calculating the required divider, and then splitting the divider into the integer A and fractional B parts to jam into the registers. The takeaway, you didn't miss a secret page. You just translated hardware speak into engineer speak. You know what? That's good enough for me. And that's telling me that I should be asking Gemini for, you know, information on these kinds of formulas more often. Okay. All right. Oh, damn. Time kind of flew by. That's crazy. Holy shit, dude. I've been busy. Between yesterday and today, I've been busy. I've been researching a bunch of things, including this clock divider thing. Dude, tomorrow we need to like we need to we need to make progress with this. We need to move forward with this. Before we continue, I need to understand how the fade effect is working, and I want to try applying my own fade effect to it, because we are essentially waiting for the fade effect to finish, right? Like, okay, let's look at the let's look at the code here. What we are doing is, if you look at HS, we are we start the duty fade, right? And then we call this, we call the while thing. So once we have, oh, sorry, once we have started this, it's going to do its thing because it has issued the, it has set the values in the registers, and the ESP32 is then going to respect that and, do the PWM thing. It's going to start doing that, but we need to kind of block the operation, for lack of a better term. We need to block the, not that operation, but we need to sort of block the loop by running a while loop for the duration of the fade running. So while the fade is running, we basically just don't do anything else. So if I did implement my own fade, I would just be doing that. I would just be increasing and decreasing um, the duty percentage, or the duty, just increasing or decreasing the duty um, over a set period of time. So I could try implementing my own version of this method, or I could just look at the code and get my understanding from the code. So let's, uh there. Okay. So we have start duty fade. Our duration is in milliseconds. Okay. There's a bunch of checks happening here. Great, awesome. Then it's taking our frequency into account as well. Or is this just a check? This is just a check. Okay. So if everything turns out fine, it's doing a bunch of checks over here. If everything turns out fine after that, then it gets our start duty value and our end duty value. And I'm assuming it more or less lerps between these two, right? That's one way of looking at it, isn't it? It lerps between these two values. I don't know what specific formula it's using here, but like, okay, since we do the multiplication first here, there's no loss of precision from using milliseconds instead of example nanoseconds. Okay. Cycles per step. What is a step here? This conversion may fail if duration milliseconds is too big, and if either duty steps gets truncated or the fade is over a short range of duty percentages, so it's too small. Returning an error in either case is fine. Shortening the duration will sort things out. Okay. Okay, so it calculates a bunch of things and then it starts this. But the thing is, wait, so we have is duty fade running, is duty fade so and so. Okay. Um, where is, okay, there's a start duty fade um function here. And I think this is what, because okay, this is starting, it's not gonna there's a function being called here, right? It's gonna jump into that function. Let's jump into do I have like a thing for jumping into the definition directly? I don't remember. What do I see here? Oh, actually, start duty fade might be in here. Let me, yeah, start duty fade, HW. Okay. So, start a duty cycle fade, HW. So that's HW means it's not taking a percentage, it's taking the actual duty value. So you have start duty, duty increment, duty steps. I don't think end is being shown anywhere here. Cycles per step. Okay. I think duty steps is the maximum amount. So maybe that's why there's no end. Oh, dude. Okay, okay. This is because now it's going down to the register level. So I should not do this. Yep, I should not do this. I should just leave my understanding to this level and move on from this. Um, yep, yep. Let's not get sucked too deep into it. Oh God, I was supposed to end the stream. Holy shit. Yeah, okay, guys, I'm gonna continue this tomorrow. I'm also gonna continue some of my research off stream, but that's gonna be it for today's stream. I'm not gonna be rating anyone today. I'm just gonna end the stream and I'm gonna continue with the research. But yeah, that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time.